You're going to thank me at the end of this lesson because this is awesome. I'm going to show you the easy way to find the equation of a parabola using quadratic regression. So this here table shows fuel efficiencies of vehicles at different speeds. Let's write a function that models the data, and then we'll use that model to approximate the optimal driving speed. So here's what we're going to do. We're going to go to desmos.com/calculator. And we're going to make a table by clicking there and then clicking on table. Then we're going to enter these here x values. La ta ti, la ta ta, la da dee. Now you might notice that these are not, constant intervals here. Here we went up 4, here we went up 6, up 4, up 5, up 5. So we couldn't use differences to determine if this was quadratic or not. So there's our x values. Let's enter in our y values. 14.5, la ta dee, 17, la ta doo. Now you might think to yourself, hey, what's all this graph paper for over here if it's not showing me these points on a scatter plot? Well, it is. It's just that we can't see it right now because we need to change our scale. Our x goes from like 20 to 70, and our y is, 15 to 25-ish. So I'm going to hit the little wrench. I'm going to change my x-axis to go from, let's go from -5 to 100 maybe. And then our y-axis needs to go up to at least 25-ish. So let's go up to, 40. That looks pretty good. And now we got a scatter plot showing these data, and you can kind of see that they're following the pattern of a parabola. Might not be perfect, but it looks pretty quadratic to me. I mean, it sure ain't a line. Whew, for darn sure. Well, can we figure out how to find the equation of the parabola that best fits these data? Here's how we're going to do it. We're going to type y1, and then at the top left of your keyboard there's a squiggly, so you got to do shift and then squiggly. And then if we would just do a times, well, you don't have to do times, but you can put x1, and right there it tries to find the best line going through the origin for that matches that data. I mean, but that's not super accurate, is it? No. If we do now push squared, now it's looking for a parabola that goes through the origin, that goes kind of through the middle of that data, but that's not super neato, is it? If we do plus bx1, it's a parabola. It's still going through the origin, but it's a little bit better. And then if we do plus c, it gives us values for a, b, and c that best fit that data. This number here, r squared, the closer that is to 1, the better that data fits. If it's exactly 1, then that means that the parabola that they give you with this a, b, and c goes right through all of the points. So this doesn't go right through all of the points, but it goes pretty doggone close, right? It looks like we missed one here, and maybe this one's a little high, but that looks like a pretty good approximation for this data. So our function then is, and I'll write it like this, f of x equals a x. Oh, here I'll write the numbers down. -0.014. That's probably enough decimal places. X squared I don't have to do x1 now because x1 was referring to this data up here. Right now I'm just getting a general function. So I'm just going to use x. And then my b is positive, so plus 1.366x plus, nope, that's a negative c value, so minus 7.144. So there's me function that does a pretty good job of, I guess since I didn't do the exact decimals, let's see if I put 0.97 there, and I put a little 2 there, and then I put a 1 there, that makes my graph look a little nicer and my function a little bit closer. And so what I can do now is I can find the value of this function at any x value. So x values are miles per hour. And so I could say, well, what's my, what would it be at 80 miles an hour? And I could just type in f of 80, and I get about 11.9 miles per gallon with that car. Well, let's look back over here. So there's me function, which models me data. And now I need to use me model to approximate me optimal driving speed. So me optimal driving speed is what speed is going to give me the best miles per gallon. So let's look back over at my graph. Now the neat thing about this calculator is you could say, well, you could say, hey, what's negative b over 2a? And that would give you the x value that goes through the axis of symmetry. And if you typed in x equals that, it would give you the axis of symmetry. What-a? Or, as opposed to that, you could just click at the top here and it gives you the vertex. 48.457 would be the x value and 25.957 is the y value. So at about 48.5 miles per hour, I get my highest fuel economy at about 26 miles per gallon. So f of about 48.5 miles per hour is about 26 miles per gallon. So me maximum fuel efficiency of about 26 miles per gallon for this vehicle is achieved at the optimal driving speed of about 48.5 miles per hour. Speaking of driving, here's an important problem for this guy. It's about how much weight can be supported by a certain thickness of ice. Because this guy does not want to become this guy. That looks like a whole lot of not fun. So let's figure out. Here they did some experiments, and we want to find out. First, we need to write a function that models the data. And then we need to find out how much weight can be supported by ice that is 22 inches thick. And you guessed it, we're going to use a calculator. Woohoo! So what I'm going to do is I'm going to leave this part alone. I'll change my f of x to just have a, b, and c so I don't have to type the new numbers in. It'll automatically get updated. I'm going to be interested in f of 22 because it's ice that is 22 inches thick, and my x values are my ice thickness. And all I'm going to change is my data. So my ice thickness is my x values. So 12, 14, 15, 18, 20, 24, 27. And then I'm going to delete these because I don't need them. Delete, 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 delete. Alright, so 12 goes to 3.4. And those are in what? Tons? Okay, yeah, good. Because 3.4 pounds would not be a lot of weight, supported by 12 inches of ice. 7.6, 10, 18.3, 20 goes to 25, 24 goes to 40.6, and 27 goes to 54.3. So let's have a little looky-loo at our graph. Seems to be going like this. And let's look at our function. Hey, look, r squared equals 1. That means that our parabola goes exactly through every one of these data points. So this is a really good approximation. And so what's it called? Function. There we go. My function is going to be 0.099831x squared minus 0.49778x minus 5.0072. And at 22 inches of thickness, we're looking at about 32.4 tons of weight as our maximum. So there's my function. F of 22 is about 32.4. So ice that is 22 inches thick can support about 32.4 tons of weight. I hope you enjoyed that lesson. It is now over. And as the demigod Maui says, you're welcome.